Thank you very much, Casey. It's always good to have friends in high places that keep track of the time. So hopefully we'll be friends at the end of this. I'll stay on time. And I want to thank the organizers for the kind invitation, all the distinguished guests here as well to attend. And hopefully the questions won't be too tough. If I may follow Professor Nakashima's motive, contains an earthquake and hide. But in any event, let me move forward. So I'm going to talk about advances in application of real-time hybrid simulation towards creating seismically resilient structural systems. So a little bit of theory, but I want to show the applications. And really the motivation behind developing this was to be able to use it as a tool. And so what I'll do is just give a brief introduction to the concept and then show you some of the advancements that really they were motivated to be able to apply this. And so I'll just focus on a few things related to integration algorithms, some state determination using an explicit form, and then actuator control, very, very important. And then the application. This will be towards something I think will fit very well with the last presentation. It's related to using it as a tool, real-time hybrid simulation for performance-based engineering. And then I'll go ahead and summarize and conclude. So I'd like to acknowledge first a number of people. I won't have the time to list them all, but particularly want to mention Professor Richard Souse, who I've known for a long time, and he's actually one of the principal investigators. I was a co-principal investigator of one of the projects that I'll show, and I have some other people to note, Thomas Marilla and Leanne Cow. We actually have an earthquake facility, real-time hybrid simulation, and they're on the staff. And the current student, who I think is going to do really good things, is Fazil Milik, and then the others have graduated, gone on to do great things as well. So resiliency, I think we know the definition. We're always trying to improve it. And sometimes this entails looking at adding response modification devices to the system. I think what's very important is to understand how they interact with the system, versus isolated tests. Now the system receives that. And so sometimes it's really required to do this by experimental validation when we can't numerically model things reasonably well to achieve a level of confidence. And so when we do that, we need to consider scale. Scale does matter. Give you an example, when you look at heat, it doesn't necessarily dissipate at reduced scale as it would in large scale. That may affect some of these devices. Low rate dependency could be very important. Realistic loading is always important, hazard level. The multi-directional system performance, you saw examples there, is very important. And then the interaction, I mentioned this, of the devices, the components with the rest of the system. And this is a little bit redundant, so seismic is the lever of the demand. It's realistic loading. But we want to be able to assign the level of hazard, so we look at performance engineering versus the fragility of the resistance. So let's just briefly look at hybrid simulation just to describe it here. So if you have a tall building, 40 stories tall, we're interested in looking at the performance of this. Could be any event, it could be wind, earthquake. It'd be very difficult to put it in your lab because the lab's not going to be as tall as the building, especially scale does matter. So what do? Well, let's look underneath the cover. We got a cover here. This is of cladding, and this is just initially wind loading. There's been nonlinear dampers added to this, so we're looking in the outrigger system. I know later there's a presentation, so I'll be very interested in hearing about this, but we want to look at the performance of the system. So what do? Well, if you model it numerically, maybe uncertainties, or you can't test the whole thing. Let's try to take the best of both worlds. So we're going to divide this up into what we can model well, call that the analytical substructure, and what we can't model well, we'll put in the experimental domain, the substructure. But we need to link the two together. So we have what's called a simulation coordinator, where each of these substructures contributes towards the resistance. This is through the equations of motion. So you have these restoring forces, capital R. The first two terms to the left of the equal sign. A is analytical. I've always called it analytical. Some people say I should call it numerical. But analytical, it doesn't have to be numerically defined. It could be some other form. And then we have the experimental. And so given a disturbance, at some point in time, that gets injected in the system. In this case, it's predefined, but it doesn't have to be. We've done aeroelasticity in this approach, but you have a disturbance. We're looking at time I plus 1. What we need to do is integrate these equations of motion such that we could issue command displacements, if you wish. And there's probably transformations involved there from the global to the substructural degrees of freedom. But you issue those commands, and then what you ask in return is restoring forces. And this has to be within the time step that you assign. If it's real time, that could be a very short amount of time. But if you're able to do that, you go to the next time step. If you can't do that, like Professor Nakashima, you want to hide because chaos could develop and things could blow up on you. But if you're able to do that in real time, that's a real-time response. So does everything have to be done in real time? No, it all depends on the rate dependency that's acquired there. And sometimes it's very difficult with the time step that you're dealing with. And if you want earthquake, if it's predefined, that gets injected right inside of air elasticity. Well, you'll see with explicit integration schemes, you could do air elasticity where you don't know the forcing function, but it's part of the displaced position. Now here's the challenge. This needs to be done in real time. It usually is the multiple of the controller speed, because a controller, everything has to be synchronized. Controller speeds are conventionally 1024 hertz, but there's some now at 2048. You have to be a multiple of that. And if you can't stay within your allocated time step, you will get chaos here. So what is hybrid simulation? Well, I mentioned real-time simulation, but the word hybrid, I think if you want to attract people's attention, call it cyber-physical, because everyone in the non-engineering room recognizes everyone outside of our realm would recognize that. Mechanical engineering, they know what cyber-physical is. So the cyber part, as I mentioned, well understood, at least numerically, could be structural, non-structural. We model that numerically, of course, and then you can have various, for a given experimental substructure, you'd have various analytical substructure models. Could be actually more than one, but I tend to lump it into one. And then the not well understood, as I mentioned, it's a little bit redundant. You model that physically with and very important, the appropriate boundary condition. Usually you impose deformations, not displacement. You've got to think of deformations, because what you expect out is forces that develop because of deformation. So there has to be a transformation of coordinates that sometimes is not so easy to do. So easy to accommodate full scale, that's not necessarily true. You have kinematics and you have flexibility and fixturing, all that stuff, but that all has to be accounted for. So we're going to have to compensate, which I'll talk about later. So anyways, at the bottom of this, I just kind of summarized what I was mentioning before. Let me move on here to try to keep track of time. So let's look at some advancements here. So what I'm going to do here is discuss this and present this in the form of, we want to implement this. It's not just an academic exercise. We really have a challenge to look at a performance of a system. So there's going to be a challenge that we need to implement. We have to develop and implement, and there's issues with this. So on the simulation coordinator, numerical integration schemes are the heart. If your heart doesn't tick well, the rest of the body knows, and it's going to present some issues. So in the integration schemes, first they need to be accurate. I'm sure a lot of us has done numerical integration as a level of accuracy you have to really evaluate. It's good if they're explicit, but then you wonder how could it be unconditionally stable? And if you use model-based schemes, you can gain a high condition of stability, and then they should be dissipated. I'll show you an example there of what that means. And importantly, is you have usually multiple workstations that exist of all these activities. You need to be able to communicate amongst those workstations. One is, say, the hydraulic controller, there may be the integrator, another one may be the acquisition system. You have to really communicate fast because the clock is ticking in real time. It's like the 2-minute warning, Ken, but there's only 10 seconds left, and you need to score that touchdown, right? So the analytical substructure, only reason it's defined analytically is because you can do that well. But you need to be able to do that well, but and do it fast, right? If you can't do that, then it needs to go into the experimental substructure, but then you may have a problem with size. You can't fit it into your lab, so that you have to consider what to put where. And then on the experimental substructure, you really should try to do as large as possible that you don't have scaling effects, and that requires servo-hydraulic power. This is usually where laboratories that are specialized, like we have that novelty, so I try to convince people to come visit us. We have the novelty to do this, but you have to have large hydraulic equipment. Actuators move off to the side rather than just going in one direction, so there's geometric issues, kinematic compensation, and more importantly, it's its own dynamics. Servo-hydraulic systems have their own dynamics, so there's moving mass, there's compressible fluid, and there's damping, so you need to account for that. And this is not easy, and shake table, same issue. Hybrid simulation has these challenges. So on the simulation coordinator, we develop explicit schemes. And when I soon developed this, he did this and he sent me a text message, I think email about 2 in the morning. I immediately called him. And he wanted to use it for just numerical integrations. I don't think you understand. If you do use this in hybrid simulation, it will be a breakthrough because the motions that need to be imposed by the end of the time step at the beginning of the time step. You base equilibrium at the beginning of the time step, and then you satisfy it at the end. So we went ahead and developed over the years. We've evolved to where the latest one is the modified, and I've always been told, I think it was Professor Wilson developed SAP, at Berkeley. He was my advisor. You want to give it some initials that may be easy to remember, but less than 3, and usually it's associated with some aspect. So it's based on the last names here. Professor Collet, who's now at IIT, Kanpur, this is his dissertation work. And so what it's based on is we use control theory. Newmark used like Taylor series and try to minimize differences in Newmark beta, but we looked at control theory. It has a lot of attributes, and you can see the kinematics here for displacement velocity are truly explicit. You see the n plus 1 on the left-hand side, the equal sign, and what you know is on the right-hand side, it's n. Alpha 1, alpha 2 integration parameters, the way we introduce dissipative characteristics is by solving the weight equations of motion. So the weight equations of motion, you can see the mass and the damping, and K here, eventually we're going to have as restoring forces, but that's associated, with restoring forces, but it's weighted. And the weights that are associated with, you see the alpha 1, alpha 2, which are matrices, and alpha 3, and then there's also some scalars, these alpha Fs. There's a lot of things floating around. And you may be well, how do I deal with all this? Well, it all boils down to one parameter, actually two, delta T and the spectral radius. But there is some mass, inherent damping, and initial stiffness, but that's based on initial elastic properties, and you could deviate a little bit from that. So you base it on the initial configurations called model-based parameters. And so the one parameter, which is very important, is the spectral radius when the frequencies, or omega n times delta t, or the big frequency goes to infinity. That's usually used in control theory, even just numerical integration. And the range of that spectral radius is 0 to 1. As a user, you have to supply a value, and you can see all the integration parameters below on that final line. There's a function that you have to provide a value. So how do you do that? Well, we've developed some guidelines here. First, I'll mention, if you decide to choose one, there's no numerical dissipation. That's not necessarily a good idea, as you'll see. If you use 0, that's total annihilation. You actually get 100% damping at the higher frequencies, but you have to look in the immediate range. Is it too much? Because what you're interested in is not destroying the contributions of the frequency range of interest that you're trying to study. And typically in earthquake injury, it may be towards a lower frequency range. So if you look on the right-hand side, we have the equivalent damping versus this frequency. And so for different values of rho infinity, the different curves show how that damping will be added. So you as a user decide, I need to have so much damping. You go to a plot like this, and for your omega n delta t, the omega n is your natural frequencies, the delta t is what you selected. You can decide on what value for rho infinity. It's also like delta t. When you do numerical simulation, sometimes have to do numerical experiments. Well, here you may want to do a pre-numerical simulation. Just want to mention, left-hand side is what's called the root locus plot. It's in the complex plane. It's using control theory, and we start right here at this open loop 0, and as you increase the frequency, it migrates around. If it's within this unit circle as a diameter of 2, it's basically a stable, what's called a transfer function, or integration schemes are converted to that. You notice it's collapsing inwards. That's characteristics of damping in the numerical integration scheme at high frequencies. That's how we basically develop this. So I remember my students had to take control classes. I made them take extra classes. I think they eventually forgave me. Now here's what's important here. If you look at this, and I'll show this more in terms of the applications, this is a 3-story moment resisting frame with a braced frame with dampers. So it's physically defined for the damper system with the braced frame, and then we have the numerical or the analytical substructure, which is a moment frame with RBS connections and the gravity system. And if you look at this is the acceleration, the ground motion. We're only looking in one dimension here. You say, wow, the earthquake subsided. What's happening here? This is the normalized moment in the RBS. It's ringing. This is the analytical substructure. You say, is that real? It's not real. What happens here is, when you study it, it's got a frequency of 1/2 delta t. It's like the Nyquist frequency. So to tell you, something is associated with the time step, and what is occurring here is you're getting nonlinearities within the time step, and this happens in any integration scheme, particularly explicit. You're getting a change of state, which in the integration schemes that causes an acceleration pulse, and usually it's at the higher frequencies. Well, that will attenuate downwards to the lower frequencies, but it's a change of state within the time step. And so these pulses will excite higher modes, and the higher modes are basically going to contribute to deformations because it's relative motions, particularly in rotations, that are going to cause or lead to the member forces. And the problem gets worse when you consider the experimental aspect, because all load cells that you need to measure response with have some degree of noise. And you say, well, it's not so bad, it's at 6 hertz, at 30 hertz, hopefully around 6 hertz. It could inject in the system and get amplified by these schemes if you don't correct for that. So the delay compensation is very crucial here to deal with that, and also with the trying to get rid of this high frequency noise. So we ran that with row infinity of 1, not a good idea. Put it at 0.75, and volume here is very important. You can hear this is the actual test, and you'll see here as the integration through develops, the red is that previous solution, the blue is now the overlay with the dissipative characteristics, doesn't destroy the modes of interest. Right, here's some animation here, and it gets rid of that high frequency noise. So of course you got to be careful, because if you specify too high value of rho infinity and it starts to deteriorate the lower modes that you're interested in, you could overdamp the system. So you have to be careful about this. So the analytical substructure, I'm thinking not necessarily shear walls, Jack, but those are important. Thinking about frame members where fiber-based elements work reasonably well. One of our solutions there for that is use what's called force-based elements, and so conventionally, there's two types, and maybe even more, of force-based elements. One of them is displacement-based. So the challenge there, the curvature varies linearly, and when you have structural members where you have inelasticity, usually forms at the ends. It's not going to vary linearly. It's going to be quite steep, and you need to then discretize the member into using more elements. So it means you have more degrees of freedom. It adds to the computations. You may not be able to do all those computations within the time step, but the state termination process is pretty straightforward. If you try to use force-based elements, the equilibrium is strictly in force, so you could really get by with one element over the length. You have to deal with the integration stations. So it reduces degrees of freedom. So the matrices, and usually matrix multiplication is a problem here with these integration schemes, and parallel process doesn't necessarily work well because you have to communicate with that process. So here, the way that's overcome is you have to use iterations at the element level. Some people have done it at the global level, but it basically gets down the element level again. Well, that jeopardizes the whole process, because it can't necessarily be complete, especially if it's done in a non-deterministic manner. If it doesn't converge, you run open siege, if you pay attention, has it converged, it will just go to the next time step, and sometimes it will blow up on you, it won't work well. So this is very important. So this is the quiz for today. I think, Casey, you'll hand the quiz out, right? I'm just joking. This is the algorithm that we developed. It's been published some time ago, but what we do is we use a deterministic approach in which within the iteration, we try to satisfy the local equilibrium as best we can. Within what we do is we select number of iterations, and the key is to carry that unbalance over at the section level, but also consider the compatibility between adjacent elements so that you get equilibrium within the element, the end of the element, and compatibility amongst the elements. And so the CO is a carryover. So in doing so here, this is how this works in real time. So, we have a reinforced concrete structure. I think it's, if I counted, I forgot, it's too early this morning to count. I think it's 28 members. We're just going to put a damper in the top. This is really trying to test out the element. This is subjected to bidirectional motions. Here we have the Kenton Park for the concrete, Mount Agato Pinto for the steel. It's 108 fibers in the cross section. We have the core, the confining core, the outer core. They're modeled differently, not necessarily using same parameters, of course, and reinforcing. And then this is how fast things have to go. This time step here, I think, was 2/1024. So as you know, concrete, and this is bidirectional loading, I don't show the axial force, but that could have, but it shows the deterioration, the stiffness, a little bit of pinching, and the energy dissipation. The upper right is the nonlinear viscous damper. Notice the force is capped, and that's going to be important when you design things. If that force kept increasing, you could have problems with the adjacent members. The energy error, we could reduce the energy error by 500,000 compared to if that carryover and that thing doesn't take into effect here. And when we compare that with the reference solution, which is numeric beta implicit, so they iterate and drive the unbalanced loads to zero. They have all the time in the world. This is all done numerically, this comparison. We get almost the exact same answer locally. So what's the impact of that? Well, if you're looking at trying to assess damage and ductility demands, the local section behavior is very important. In terms of experimental substructure, I already mentioned servo control is important. Just to emphasize this, if you look at an input signal, this is displacement versus time on the right, you desire to have the red curve follow the actuator, but it's going to be some delay, but also maybe amplitude error. So I'll just express it as such here. There's a delay of tau and amplitude error. If we expand that in Taylor series, we'll have this form, and then let's try to express this where we're going to try to adapt and have coefficients. So our goal is to use what's called the cost function, minimize the difference between what we need to assign to the actuator to get where it's supposed to be. It's like driving your car and pushing harder down the accelerator so you can get through the light before it turns, I guess, red. But then you have to estimate that. And so we're going to try to minimize this cost function. This is going to lead basically to enabling us to get the coefficients. Now the important thing here is on the feedback, we use the specimen position, not the actuator position, because you can have error due to slop in the fixtures, other things. So we measure the position of the specimen. I think that's very important. And so this is just expanding. I've got an infinite number of coefficients. We keep it to 4 actually. So this is called a jerk, which is a derivative of acceleration. And more importantly, as I said, we use the specimen displacement. Typically we actually use numerical derivatives, and we have to filter that, but we filter both the input and the output to get rid of the delay effect here. And so it just boils down to least squares, regression analysis. You can get these coefficients, but there's a moving window that lags 1 clock tick behind. The only reason the window's not bigger is because you don't want to influence too much what's going on now versus the history too long ago. But also computationally, the matrices get too big. You can't do this in real time. Now, what's important about this is no user-defined gains, but you probably want to have ceiling and floor limits. It's probably not a bad idea, so you just don't keep adapting the actuator just all of a sudden doesn't accelerate too fast. So a good example of this, because you can't pre-tune these necessarily, especially for concrete structures, it may be very sensitive to small amounts of motion could actually change things, and then there goes your test specimen. So the adaptive scheme works pretty well for that. And most importantly, it negates time delay, which is the most important, but also amplitude. And you can relate that to the coefficients. They have a physical meaning. So first coefficient, the inverse has the amplitude error that you corrected for, and the ratio of that divided into that second coefficient, H1, gives you the amount of delay that you're compensated for. And so I'll show you some examples here in this application now. And here we're going to look at the same structure showed before. We're going to look at the performances under the design basis and the max considered events, which have roughly these return periods here. So the structure we looked at here initially was designed by ASC 710, because this was a few years ago. And the floor plan is shown on the left. It's a 3-story, 6-bay by 6-bay office building located in Southern California. I think it's near Van Nuys there. So we had to do deaggregation, choose all the records for the seismic hazard. The system is a moment-resisting frame of RBS connections. And then there's a damp-braced frame, as you'll see, to control the drift. And we accounted for that, the gravity system, and the inherent damping, which was about 2%. And the moment frames now are designed for strength. And when you design things, you need to design for strength, but also need to design for drift control. We said, no, we're going to use the moment frame design for strength. And how do we control the drift? Well, we use the dampers to control the drift. And in this case, we chose 2%. So we're going to look just in the one direction, east-west. This is a seismic tributary area, and looking at the elevation, these are the two lateral load resisting systems, and we consider symmetry in the tributary area. This is the test structure here. Gravity, moment frame, the damped brace frame. And the dampers were nonlinear viscous dampers. This is characterization test. You can see the rate dependency there. The system, we couldn't choose full scale because why? Because the crane only went so high, about 50 feet, and we couldn't construct the last floor. So we went as large as we can, 60%. You can see the students here are working on, it's the orange. The thing on the outside is our version of the bird cage, which is a test frame to stabilize the structural system so it works in the plane it's supposed to. There's a close view of the of the dampers, and then the analytical and experimental substructure. We used these force-based fibrillants, had also panel zones and p-delta effects. We didn't have to use a co-rotational formulation here because the drift was less than, in fact, less than 2%. It worked quite well. And then here's the, the video here. I think some of this is self-explanatory. These are the 3 dampers and the 3 floors. This is the analytical substructure, RBS. We had to discretize quite a bit because the flange width will change. This is the RBS. I'm sorry, this is the damper of the first floor. This is the story drift. Story displacement, I'm sorry, versus floor. And so if we looked at that, this is for the different earthquake. I don't remember which is Chihshang, but you have it in the paper. But this shows at the end of the simulation, very minimal floor drift. This is for the design basis earthquake. Now we did several phases. I don't have time to go in the other phases, but phase 2, where we put everything in the lab except for the gravity system. And we essentially got the same answer, which means that we must be doing something correct here. So real quick on the adaptive compensation, we have the targeted, the compensated, the measure, the target, and the command match very well. This just shows this. The best way to assess this is to look at synchronization subspace plots in which you look at the measure versus the target. And that measured should be everything that's included so that that structure where it gets to where it's supposed to be. You measure that will assess the delay. And here the RMS error is very good. It's less than 1%. And then the compensation, you see each floor, the different coefficients for each actuator, they're all varying. So this servo hydraulic system is changing in time, primarily because the structure and also the dampers are not, they have different characteristics. The amount of amplitude correction and delay compensation. If you say, well, okay, 18 milliseconds is pretty small, right? 35, but look at the time step, that's only 3. If we didn't correct it, we wouldn't have made it through the earthquake because you're going to put energy in the system and it's just going to blow up on you. Now, in this system, what primarily yielded, if any, was damage in the RBS beam-to-column connections. But it was mild, as you see. So we can repeat this many times because we can model that analytical substructure of all that damage numerically. Experimental substructure remained linear. So we looked at record variability. In the paper, I think the records are listed. If not, it's in this paper here. That one of these was the Chihshang. And we scale this to these 2 hazard levels. We looked at different levels of design. This is going to be very important. 100% design-based shear, you can go down to 75%. I think Andrew knows that quite well, but we went below. So why 75%? Has that ever been verified at system level? We went down to 60%. And we did these simulations. The second floor had the most, this is now the mean statistics, the most peak drift, but it was rather small. This is 1.17. The MC is 2.21. The target was 2% or less. Look at the residual drift. There's hardly any residual drift in the design-based earthquake. Even the MC, which goes back to what Professor Nakashima showed, I think we could control that if you do it right with dampers, but you have to consider a number of other things. What are the other things? The phasing between the dampers and the rest of the system. They're not out of phase, as sometimes people believe, particularly in the design world. This is now the damper force plot against deformation, but also the damper force plot against story drift, the red and the blue. And you notice that when the curves reach their maximum drift, the damper deformations are such that the story drift's larger. This indicates there's elastic flexibility in the load path. This is very important because the damper force is basically near the peak or not going down to 0. The velocity is supposedly 90 degrees out of phase. They're actually almost at a maximum. So you need to account for maximum damper forces maybe at the same time as maximum forces from the elastic drift or inelastic. And this is exemplified if you look at the PM interaction for the braced frame. This is in the column. You get maximum moment. You're almost at the maximum axial force. Actually, it's increased because the dampers, and this is very important, particularly in reinforced concrete structures. You just throw the dampers in there. You need to account for the fact you may increase the axial force significantly, and the columns could fail in compression there. So this phasing is very important. And so it needs to be accounted for really in the design. And this is documented in some of these papers here. So just in summary, you could control the drift without increasing accelerations. If you decide I'm going to control drift by just throwing a bunch of stiffness up there, you're going to raise the acceleration. So that's going to be important. And we showed, relative to conventional frames, even though I don't show it here, we got much better behavior. But again, that force path, that elasticity needs to be accounted for. And with the reduced design, we demonstrated that it can perform well. And if you have this kind of performance level, in the US we look at immediate occupancy and life safety and collapse. These perform immediate, and if you look at the MC, maybe someplace between immediate and life safety there, but they performed well. Significant better performance than conventional MRS without the dampers. And overall summary, tried to illustrate these advancements, and they had a purpose. We had a goal in mind, so we had to go back and do the development in order to achieve this. And that the application could be applied to large systems. It doesn't necessarily have to be earthquake, but I illustrated for that and try to demonstrate the advancements there. And I think these, in the future, this could be used as a tool, in real time for looking at hazards to try to improve resiliency, not just earthquake, but wind, storm surge. That's some other things we're working on. And I just want to acknowledge the sponsors, National Science Foundation. They sponsor, we have a NERI facility network for natural hazards for earthquake research institution or experimental research infrastructure, sorry. We focus on multi-directional simulation. This is the sponsor, NSF, with the grants, and that particular research was supported by NSF, the dampers. Richard South was the PI. He and I worked together quite a bit on things. And the dampers were tailored devices. You maybe saw the logo. They were provided for us. And with that, I want to thank you.